Good morning, good afternoon, good evening, everyone. I'm Ira Feldman. I'm the Executive Director of MEPTEC, and I would like to welcome you to today's Semiconductor Industry Speaker Series produced by MEPTEC and IMAPS. So thank you very much for joining us. We know that there is so much going on this week between CES, ISS, and the drama on C-SPAN. So we very much thank you for joining us today. And we have a great presentation. And so do some intros. The next two speakers for the Semiconductor Industry Speaker Series we're working on. We have some very exciting prospects that we just need to finalize, including one from a hyperscale data center company. So we will announce them as soon as they are available. And on March 10th, we will have John Park from Cadence Design Systems looking at the difference between heterogeneous integration and system in package from an EDA perspective. So we look forward to these presentations. We're also always looking for other speakers. So please let me know or Dave Town know if you're interested in speaking at a future webinar or a luncheon when we can resume those. We also are very proud to announce the Too Hot to Test. We're looking at the thermal management of ICs during testing, especially with the very large die for advanced computing. These devices are getting hotter and hotter. And the schedule and registration have been posted. They just opened today. You can go to events.meptec.org to see the agenda and to register for this free event that is courtesy of the sponsors. We have a great program. It'll span all 3 mornings, February 9th, 10th, and 11th. And you'll also receive email, and there'll be more information on the meptec.org website shortly, but you can get a sneak peek and register today by going to events.meptec.org. There will not be a speakers series presentation on the 10th because of Too Hot to Test, but look forward to having you join us at Too Hot to Test. In terms of MEPTEC, we are a membership organization supported by your membership and corporate sponsorships. So if you haven't renewed or joined, please do us the favor of doing so that we can keep producing events and making them available to everyone. If you have any questions, please contact Betty Cooper, bcooper@meptec.org. Today's Semiconductor Industry Speaker Series is sponsored by Toray and ASE. For those who are not familiar with Toray and ASE, I'll tell you a little bit more about them at the end of today's presentation, but we'd like to thank them both for sponsoring today's presentation. And similarly, if you're interested in sponsoring, please give Rosina an email. Thank you. So today, our speaker is Jan Vardaman. Her presentation is Outlook for 2021. Are there supply limitations to growth? Very happy to have Jan here. She almost doesn't need an introduction, but I will introduce her nonetheless. She is the president and founder of TechSearch International, which she started in 1987 to provide market research and technology trend analysis to the semiconductor packaging industry. She is an author, a frequent columnist, a lecturer, and speaker and presenter at many industry events. And prior to founding TechSearch, she was on the corporate staff of the Microelectronics Computer Technology Corporation, MCC, the electronics industry's first pre-competitive research consortium, doing really great work for the industry there. So I'll turn it over to Jan in just a second to answer the frequently asked questions. Slides will be available next week. You'll get an email. They'll be available on meptec.org, and a recording of today's presentation will be posted to the MEPTEC YouTube channel, youtube.com/MEPTEC Presents. So feel free to subscribe there. but we'll let you know when that's available. And in terms of questions, Jan will take them at the end of her presentation, but please put your questions in using the Q&A tool, and then we'll sort through them, and I'm sure we'll have a very live discussion. And with that, over to you, Jan.
Thanks for the introduction, and Happy New Year and greetings to everybody. And thanks for joining us today. I hope we can have a really nice discussion at the end. So, what I want to talk to you about is kind of our outlook for 2021 and kind of what the limits are, the supply limitations to the growth in our industry, because 2021 surprised a lot of people with our growth in the electronics industry, despite the fact that we had a major pandemic and a lot of bad things happening around the world. So we are fortunate, those of us who are in the electronics industry, and were able to work and keep our jobs. So anyway, let's start out by talking about those growth areas. Um, we've seen obviously the data center and cloud computing expansion continuing, driven by events just like this one, where we have a lot of people trying to listen to discussions, do virtual conferences, do business meetings, and all kinds of things like that. And what this has done is really driven the demand for servers, for server CPUs. It's driving the demand for DIMMs. It's driving the demand for AI accelerators, integrated photonics development. And it's also, we've seen the demand for AI accelerators and networking increase, which has driven our demand for HBM. In a report that we just released about in November, we've reported that there was about a 49% growth in wafers for the HBM, including the memory and the logic, from 2020 to 24. So that's tremendous growth in this area. The AI accelerators, and we're seeing still the use of silicon interposers, networking increasingly on the Fanout on substrate, and we're seeing a lot of discussion of bridge solutions. So lots of driving a lot of different packaging developments. As everybody knows, the laptop and tablet demand sales growth was really strong, and much stronger in 2020 than we expected. And that continues to be driven by the work from home and the educational demand, as we still are in this pandemic. Gaming systems have also been popular, very strong growth on that. We've seen the announcements for some of those gaming systems being basically out of stock because so much demand. Growth in 5G infrastructure hardware has really supported our industry in 2020. While the smartphones were not so great for 2020, the 5G smartphone growth is really projected to help us in 2021. So a lot of these, some of these areas are continuing from the 2020 growth we've seen, but then there's also some uptick in based on a lot of our 5G smartphone, and that's one of our segments that we always are is important because of this so much of the package use in that. And then the auto industry is also returning to growth. So let's talk about a few of these in more detail. In the integrated photonics, we saw Intel announce their co-packaged Ethernet switch with the integrated photonics engines. And while these are not huge volumes that people are talking about, they're very important in enabling the data center services. And so we're going to see, this trend toward development work and deployment over the next several years, starting with this year that we're in now. Our 5G infrastructure rollout is continuing. We noticed that the China Ministry of Industry and Information Technology says that they installed about 710,000 5G base stations last year. Now, this is, I'll remind you, is the sub-6 gigahertz, which is what they're rolling out over there. They're planning to install 600,000 base stations this year if sufficient components are available. Now, a lot of that was the Huawei systems. And as you remember, there's the embargo for selling things to Huawei. So there was a very large stockpile that Huawei had in 2020. So if that stockpile is completely depleted, it may be difficult to reach this goal of 600,000 in 2021, but nonetheless, that's the goal. And this would, of course, drive demand for RF modules, system and packages. And our rollout continues in the US and Europe. That is a millimeter wave rollout. So that's more of your antenna and package designs. That's also going to drive our small cell growth because the millimeter wave requires the small cells to transmit the signal. And so we're going to see a lot of continued activity. The licensing and things were slowed down a little bit in 2020. That seems to be picking back up. So this 5G rollout is a multi-year kind of rollout that we expect to see. And this drives our complex SiP demand, the laminate substrates with antenna and package. So it's a very busy time for people that are in that space. Now, our smartphone growth, as reported by IDC, is expected to be driven by the 5G sales. And you can see in this kind of magenta part of the graph that shows this very large increase in 5G sales over the next several years, especially from 2020 to 2021. And so this is a lot of this now this will include both the millimeter wave and the sub-6 gigahertz. Our cell phone growth in general, of course, was down in 2020. Some people have said it was down as much as 9–10%. And IDC is projecting that the growth in 2021 for the overall market will be about 4.4%. So that's a pretty good growth rate for our smartphone compared to the fact that we had a large decline in 2020, which is really an unprecedented decline in smartphone sales. So this will be very good for the industry because we have so many components. And with the 5G introduction, we've documented through a lot of our teardowns that there are many more components in the 5G, especially the millimeter wave phones, and that will drive growth in the industry, both for the production of chips, the packaging of chips, so that should make the OSATs rather happy. Automotive market, we saw the worst slump in history in 2020, a 20% decrease in vehicle sales. Why would you buy a car? You had no place to go. You're in lockdown. But we're expecting to see that return to growth in 2021 with as much as an 11% increase in vehicle sales. And it's a surprisingly large increase, and it's kind of caught the industry a little bit flat-footed. There's a lot of growth projected for EV sales, the electric vehicles. And so this growth, whether we can achieve this 11% increase in vehicle sales, will depend on whether we can get components. And we'll talk about that a little bit later. The New York Times article today talks about the difficulty of getting some of the components for the automotive industry to meet this really ramped up demand. We also see that, because there's more and more electronic content per car, we did continue to see a growth in our adoption of the ADAS, the cameras, radar, ultrasonic, and we'll see LiDAR continue to be worked on and rolled out in the future. So it's a lot of exciting times in the automotive industry and some concerns as well. Now, finally, after so many years, the industry has recognized the importance of packaging. We have realized that the economic advantage of silicon scaling is gone. It's very high cost to move to the next silicon node. And this high cost of fabrication, as you know, includes the design, mask, and the fab process itself. So, and there's only a limited number of the foundries that can afford to participate. And there's a very limited number of companies that can really afford to pay for these advanced nodes. So one of the things that we've seen is we've realized that heterogeneous integration is providing an opportunity to achieve the economic advantages that were lost with the end of pure scaling. And there's a variety of package options for this, including, especially in the high performance area, including things like silicon interposers, Fanout on substrate. I'll speak a little bit more about chiplets in a few minutes, and a lot of variations of 3D stacking. So this heterogeneous integration, the smart packaging, is really helping us to achieve the economics that we can't achieve with pure scaling. And I think that that's really been recognized in the industry. And I do hope those people over at the ISS are talking about this as well and not so focused on the front end that they've ignored the back end like they always do. Heterogeneous integration, especially chiplets, is really offering improved basically signal performance, power, lower inductance, thermal resistance, form factor advantages. So tremendous advantages in this packaging trend adoption. And we also note that people have now realized that co-design of silicon package are absolutely essential. You simply cannot design the silicon without keeping in mind what that package it's going into. And in some cases, you're actually designing the package with the silicon, as we've seen in some of these new chiplet designs. So let's take a look at some of the things that have been happening. We've noticed that still the silicon interposers are one of the most mature technologies offering the highest density die-to-die connections for a side-by-side package configuration. So this is, because it's a very mature technology, we've still seen a lot of volume in this area. TSMC has 10 years of silicon interposer production and assembly, and we've seen an increasing size of the interposers with multiple HBMs and multiple die in the HBMs, with up to 8 die expected to be common, very common this year, with people projecting up to 12 die in an HBM and 12 HBMs. So a lot of die. So you can see why we would see such strong growth in the HBM space. Also, we've noticed that in some conversations I just had with the new vice president of Samsung in charge of technology, that Samsung is seeing more applications for the silicon interposer solutions. And so we'll see strong adoption of that. So a number of people, not just TSMC, are seeing the increase in the silicon interposer design. We also have a lot of interest and expansion in our fan-out on substrate. ASE has been in this space for quite a long time with their focus, their fan-out on chip on substrate, RDLs with 2-micron line in space. Obviously, if you don't have to use a silicon interposer with those super, super fine features, you can use a fan-out on substrate, and it would be a less expensive solution. Typically, for some of your high I/O counts, ASE has both a chip first and a chip last solution. TSMC has their integrated fan-out, which is called the Info R, with R standing for RDL. The RDL with 2-micron line in space, maybe 3 or more RDLs plus a UBM. Amkor has introduced a chip last solution, which is the Substrate Swift version, that's also capable of achieving having the RDL with 2-micron line in space, up to 3 RDLs plus a UBM. And of course, I just mentioned that in the roadmap you saw previously showed that Samsung has also introduced their RDL version as well. So what we're seeing is we're seeing more and more people look at the designs for these packages moving forward. And so we'll probably see more of this start rolling out in 2021. We had a lot of people looking, making their plans, but now I think in 2021, by the end of the year, we should see a lot more of these packages. Now, we've also had a lot of interest in this embedded bridge technology. And the embedded bridge developments, we were surprised by how many that we found when we were working on our last report that we rolled out in November. Basically, Amkor has an embedded in the RDL, a chip last solution that they proposed, S-Connect. ASE has an embedded in the RDL, a chip first solution. IBM has embedded, which they discussed a little bit at Semiconductor Taiwan last September. IBM has introduced their embedded in laminate substrate technology. They are offering some licensing on this and working with people that would like to use this as well. Intel has their EMIB technology, their embedded multi-die interconnect bridge. So that's probably the one that people have heard about the most. They've been in production with that for the AI accelerators for some time and are expected to use that for their server applications next year. So there's also SPIL, which has an embedded in RDL, a chip last version. TSMC has embedded RDL for the fan-out. They also have an embedded version with a silicon interposer CoWoS. So there's a lot of introductions of embedded technology, embedded bridge technology, and the idea being that you don't need to fab the whole area at a super high density. You just could use the bridge to only have the high interconnect density where you absolutely need it. And of course, we've covered this in a number of our reports and presentations in the last year or so, and we'll continue to cover this exciting area. Chiplets. Let me talk about chiplets. Chiplets TSMC argues that chiplets are a key enabler for the next 10 to 20 years. And I would have to agree with that statement because of what we've seen in our interviews that we're conducting right now for a report that we're about to introduce. This chiplet demand is being driven by the need for a more cost-effective solution given these challenges that I talked about in scaling. The desire to reuse IP, but by being able to reuse IP, there's a lot of savings, of time to market, cost reductions, and all that are all possible. And we've seen a tremendous amount of data that shows us that there's improved electrical performance and reduced power consumption. And believe me, reduced power consumption is important from everything from servers all the way down to your portable electronics like your phone and your laptop. So this is driving a lot of adoption as well. And of course, there are form factor advantages too. Now, it's really important that we have a robust ecosystem for this. We have really seen a lot of work from the EDA tool and modeling capability, and I think that you'll hear John Park talk about that coming up in your March presentations. But it's also important to have adequate supply substrate capacity for this. Our thermal solutions, it requires a lot of design work on that. This is not trivial, especially when there's a 3D version of it. And you need to have a test strategy for this. So some of the famous things that have been introduced, I think AMD is in their third or fourth generation chiplet design on an organic substrate. TSMC has introduced their SOIC, which is supposed to move into production this year. That will be very exciting. This is a 3D version where we're going to have a chip stacked on top of a chip. And so these are very interesting developments. And I think more and more we'll see this used throughout the industry over time. Intel has introduced their version of a chiplet called the Foveros technology. Now, in this case, there's an active interposer. So what you're doing, instead of the passive silicon interposer that we talked about in other presentations, we're talking about the possibility of putting active circuitry, things like power management features, voltage regulators, the PCH functions, if you will, sometimes. And the benefits of this are reduced voltage drop, power efficiency, more immediate power delivery to the CPU cores because of this proximity, elimination of passes on the substrate, and a system-wide communication off of these multi-chiplets or versus the limited die-to-die communication that is there with the passive silicon interposers. And so we've actually seen this introduced in the Samsung Galaxy Note S, which is a mobile PC, and it has reported to have longer lasting battery life. There's no fan in the product. It's a very thin package, allowing a very thin product. So we will probably see this roll out in other applications as well. And I think one of these key points that I want to keep reminding people is this power efficiency being a really, really important driver. Now, we're also seeing our 3D integration moving forward. As I just mentioned, the Intel Foveros is using the die place, the first versions that are in production now, and we just did a teardown of that laptop to take a look at this. The die are micro bonded to the active interposer. Intel is working in the future with the use of hybrid bonding. They have a joint agreement with CEA-Leti. And a lot of work going on to bring up the hybrid bonding, which would be a no bump. It'd be a direct connection, direct bond connection. TSMC's SOIC and their wafer-on-wafer processes are designed to handle less than 10 micron bond pitch between chips. So what this hybrid or direct bond interconnect or whatever you would want to call it is going to do is it's going to allow you to have a very, very, very tight pitch. It also has some good performance advantages that we will see as we look at some of the amount of data that's being presented in papers from these various companies on what they're doing. We have new forms of 3D IC from Samsung, including SRAM plus logic, and we'll see more logic and logic. So we'll see this stuff start rolling out more and more this year and moving forward. So it all sounds great. Sounds like we've got a great year ahead. So what could go wrong? Well, a lot. First of all, we have a lot of laminate substrate demand that is being driven by things like our data center and cloud computing. This is increasing, as I mentioned, our server volumes. So that's been driving our flip chip BGA substrate capacity expansion. These layer counts could be anywhere from 18 to 20 buildup layers. So they've increasing very high layer counts, much larger body sizes. And so it's sucking up a lot of that capacity that's available. And we've also seen, as I mentioned, the AI accelerator demand increasing. We've heard TSMC talk about their CoWoS expansion, the Fanout on substrate designs from ASE, Core, TSMC. And I'll remind you that whether it's silicon interposer or whether it's a Fanout on substrate, there's a laminate substrate on all those parts. And some of those have very, very high layer counts, and they're very large. If you look at the network switch products, those are increasing from what had been like a 55 by 55 millimeter part to a 75 by 75 to 85 by 85, with these people driving up to 100 by 100 millimeter body sizes and increased layer counts. So that's really driving a lot of demand for substrate capacity. And of course, we have a constraint. First of all, we had a fire that damaged the Unimicron substrate facility in Taiwan, as you recall, in October. And that made the substrate capacity problem worse. It didn't create the problem, but it made it worse. That plant was supplying flip chip CSPs, including antenna and package substrates. Unimicron did transfer production to other facilities, but some companies were having trouble finding capacity. The fire also damaged a portion that was a non-Intel flip chip BGA buildup substrate production because Unimicron was using, we understand they were using the lamination process that was in the flip chip CSP area for the non-Intel flip chip BGA substrates. So with that gone, that caused a real big issue there for people. Now, there's very little flip chip BGA and CSP capacity available anyway, because we've had big demand. And in many cases, any capacity that is available from non-traditional suppliers, such as the one company that's in the US that was the IBM Endicott that became i3 that was purchased by TTM and is in Wisconsin, is basically a different material set. So the primary material is the Ajinomoto buildup material. Also, the Sekisui material has been basically qualified in a couple of places, and BT resin is one of the main materials that's used for companies as well. So those are the qualified substrate suppliers are, the ones that most people have in production. The qualification process, as we found, for a new substrate supplier and materials is very long and expensive. So we've been discussing with one of the sponsors of this webcast, Torrey Research Center, to see if there's any way that we could speed up that process. Their facilities, their analytical facilities, were not shut down during the pandemic, and so we've been having some discussions about how possibly we could maybe do some things to improve the qualification speed. But right now we're talking about a qualification process that's something like 25 weeks or $250,000 to qualify a new substrate vendor. So, that's a challenge. Now, some laminate substrate equipment has a long lead time of up to a year, we found. So that means that if you did want to put a new plant in, it might take you a year to bring that, to get the equipment to put into that plant. So we expect capacity to be tight at least through the end of this year, despite the fact that some people have said that they're going to try to increase capacity. And what's happened is that the prices for the IC package substrates are increasing and lead times have stretched out. We've heard people talk of as much as, something like 30 weeks kind of time frames for lead time. So it's really discouraging in the industry to see this. And so you ask yourself, well, why haven't people, realizing that all this demand was there and continued demand, why haven't people invested? So we asked that question. And the substrate, basically what we looked at was the level of investment required for this next generation substrate is really difficult for the substrate manufacturer to meet with their current revenue stream. We took a look at the financials. And if you look at what's required for that advanced substrate line, it could be up to $300 million for substrate capacity to support, say, around a 5 micron line in space or something like that. And so these substrate companies have relatively low margins. Why? Because we've been beating the crap out of them to get lower prices because everybody wants lower prices on everything. So if you look at some of the traditional substrate companies that mainly make substrates, you'll see that like people like Shinko and Kinsis and Unimicron have fairly low gross margins compared to other people in industry, even lower gross margins in some cases in the OSATs, who often complain about the difficulties, and then much lower than our foundries or our IC substrate IC suppliers in general. So the level of investment needed is not something that these substrate companies are comfortable making if they don't think that the capacity will be utilized 2 or 3 years from now, because they need to get a return on their investment. And it's going to be very difficult to do if they think there's going to be a decrease in demand. And what happens when they invest in too much capacity? Then prices fall, they can't make their return, and their margins suffer. So it's a really tough situation, and it's a I would say that we're in a really bad situation in our industry because of this. So what could we do? Well, a lot of times when you can't get what you need, you'll remember when you put your Instacart order in and you wanted to get something from the store, the grocery store that was going to be delivered to you, they'll make a substitute. So if you ordered broccoli, you might get rutabagas instead. So while the substitute process for substrates is not quite that bad, you could substitute things. You could have some substitutes like maybe a fan out on wafer level package. Remember, one of the reasons that the fan out on wafer level package was invented was there was no substrate. And so people considered the EWLB was designed to be a lower cost option, no substrate, no bump. And so companies are kind of considering maybe this might be an option to deal with some of the smaller size CSP type substrates. And the market had already shown an increase in our analysis that we did several months back of 15.5% growth in units from through 2024. And this is applications including mobile devices such as the automotive radar, the high performance computing and telecommunications, as well as all of our mobile products and the Intel, the Apple Info process that's used in the Apple, both the smartphone and the watch. So there is some discussion about, well, maybe we could shift some things into this other package that doesn't have a substrate. And certainly people are looking at if there's a package that has two substrates, how can we cut that down? And a lot of different discussions going on about how we can get a substitute or another plan in place. Well, what about if we had some kind of yield improvements? You know, when you look at the foundry guys and the fab people, one of the things that they've learned very quickly is if you can increase your yield, for example, when they've decreased the die size, they've got more higher yields because of defect density, and they're able to get more die per wafer. So that's a lesson that we've seen from them. So what if we could do something like that and have yield improvements in substrate production? If we could get more parts per panel, that would allow us greater capacity. So a lot of these very complex substrates with high layer counts and fine traces, they have lower yields. So if we can do something where we can improve the yield, maybe that's faster than, or could it be faster? It's a question really for the audience. Could that be faster than trying to put in a whole new plant by doing yield improvement? Now, could we do process improvements to allow more good parts per panel? Do we have some metrology developments that we could work on? And so that's really a good question for what can we do in the short term other than just try to just add more capacity, which we need to do anyway, probably. So a good discussion for people to have. So in conclusion, I'd like to say that the industry really needs to improve the health of the supply chain. I've talked a lot about the substrate, the laminate substrate business, but there's other areas that are also supply constrained. Lead frame companies have also exited this market because they couldn't make a profit. There are people that are still at this point, Sumitomo Metal Mining, with their operation in Taiwan is closing some Japanese production facilities. Other people have closed operations for lead frames simply because they just couldn't make enough money. So now what we've noticed is that lead frames are in short supply. Chip capacitors a lot of times haven't added capacity because there's been no margin or limited margin. So if you think about the cost of a chip capacitor, anywhere from say 3 cents to 15 cents, depending on which kind you're using, you could not be able to you may not be able to ship a system, simply a very expensive system, simply because you can't get one of these chip capacitors. So we've seen that happen before, and that could happen again. Because basically these people didn't get margin on it, so they didn't add capacity. Also, part of this automotive problem that I think the New York Times article referred to today was dealing with the 200 millimeter capacity, wafer capacity, which has been a concern and a constraint that we've been dealing with for a while. And I think that's gotten worse because we've had these geopolitical conflicts that have shut off some of the supply from people like SMIC, which is a big 8-inch wafer capacity, into the supply chain. So there's disruptions that are kind of beyond the technical and business control that have also maybe causing some concerns. So, if you look at if you've got this huge unexpected automotive demand growing, and the New York Times article talks about how that they're unable to get all the chips that they need to meet that demand, we might not be able to have that growth that we've projected for this year, that IDC and others have projected, or many companies, iSupply and other people have projected for the automotive industry. And I would argue that this business model for the IC package substrate is basically broken. We're going to have some kind of new approach to these business relationships to guarantee supply. We have beat these poor substrate suppliers practically to death on pricing. They have not been able to maintain their margins. It is not a healthy situation. And they really have to be able to maintain sufficient revenue to invest in the next generation. So I think that the industry as a whole, at the start of this year, we need to have some discussions about what we're going to do and how we're going to make this supply chain work for us so that we can meet all these excellent opportunities that I presented in the first part of this presentation. So with that, I'd like to thank you very much, and I hope I've saved a little bit of time for questions.
Thank you, Jan. And yes, there are a few questions that have queued up, but before I get to them, I mean, we've heard the story over and over again in the electronics industry where, part of the supply chain gets beat down to low margins, and it never seems to be on, quote, management's radar, the health of their supply chain. And then people get cut, they get short. Yeah. I mean, how do we get the companies to learn?
I think this has actually managed to make it to the CEO levels for discussion. So like I said, packaging has all of a sudden become much more important. People have realized the importance of packaging. It's elevated to the corporate levels in companies and semiconductor companies. And I think that, that we're understanding that we need to do something in this situation now, because we really are at a juncture in our industry where we just simply can't meet the demand without our supply chain in a good position.
So does it come down to anything, and this was one of the questions here, does it come down to anything more complex than just letting them raise their prices?
It's a little more complex than that. I think you have to improve the existing relationships, because one of the things that's very important is if you can work with the substrate manufacturer to do things to help them improve the yields, whether it's helping them with their process yields, working together on that. I think that that's also part of this, as well as allowing some price increases and not trying to beat these people down to death. And you folks out there know who you are when you're beating them to death. So, I don't need to name names.
Okay. And related to that, one of the attendees is asking, is there any possibility that any US-based substrate manufacturing will come online to provide enough supply?
Well, now one of the things that we did when we looked at the where these substrate suppliers are located, they're located around places where there's infrastructure to support that business. Now, as I mentioned, we do have a U.S. supplier in Wisconsin. That's the operations that were moved from Endicott. But that material set is a completely different material set from the material sets that are used in most applications. And remember what I told you, it takes 25 weeks, $250,000 to supply to qualify a new substrate vendor, especially with a different set of materials. Um, so maybe you could do something in the US, but you'd need to locate things where you had the existing infrastructure to support that substrate business. So you'll look regionally around where these things are in Taiwan and in Japan, and you'll see that they're clustered around areas where the support network is there. So it's not a simple, and not only that, you need to have people that have the process capability to do this type of work. This is not just pick up somebody off the street and train them to work in a substrate line. And these things have to be clean rooms. They have to be, I mean, there's a lot of things that go into this. There's no quick, easy answer.
And how does reshoring, I mean, obviously there's the geographic centers and, the supply chain, but is the reshoring, activities in the US and Europe going to change any of this or?
Well, I think it's commendable that people are finally paying attention to the situation, but it's more complex. The problem is, and I wrote a column in the magazine, the PCB Fab and Design and Circuits Assembly magazine the other day, and talking about R&D and the importance of R&D. And I quoted from the CEO at CEA Leti about that the R&D is like the roots of the tree, and we've neglected R&D in this country. So we've neglected a lot of things. And this isn't instant noodles here that politicians think you can add hot water and get something going. I mean, this is more complex than that. And people need to sit down and have a serious conversation about what it really means if you want to reshore things and you want to do things. And it's not writing a quick check at it and then turning your back on this stuff. So there's a lot of complexity that goes into this, and a lot of discussion needs to take place. Yes, maybe we're at a good starting point, but you know, more needs to be discussed.
Okay. And you talked about, the yields of like example, the substrates. I mean, how much of this is a function of the complexity of the packages? The person asking was, these the exotic packages, how are they faring in tests? And, is the real cost of the multi-chip packages the low production yields unless all the chips are
Well, I
perfect?
mean, what I was speaking of specifically is when you have, look at a build-up layer that's a sequential process. So you're adding all those layers as you go through your production in your substrate. So that means that if you have a defect on the first level, that defect, when you put 8 layers on it, is still there, and you may not even know it's there until you get to the end. So then when you get to the end of the line and you test out this substrate, um, it's not good. So your yield is low. And also when we talk about the embedded bridge substrates, that's an embedding process. So there is actually there is a yield hit when you embed things in a laminate substrate. So there's all those discussions as well. And I think that complexity, I mean, there's maybe I've often asked, is it possible that we could do some less complex substrates? But when you get to the fine feature sizes, maybe that's challenging. But perhaps some of these new designs in the future will allow us to do something. I think that remains to be seen.
Well, and that's the substrate side. I think the person was asking, okay, now we have multiple die in a package. That's more complex and the quality of the die. And we talked a little bit about this at the Known Good Die workshop where you did an excellent presentation, but how much of that is driving the cost or the capacity because you've got to throw away a certain number of
Sure. Sure.
packages
I mean,
because of yield?
you'd really like to not have to throw, I think that our industry is at an inflection point where we are realizing that we're realizing what the front end fab people realized a long time ago, that the metrology and the attention to that and the spending on that has become really important, and we're really going to have to invest more in that moving forward because you can't afford to just continually build more plants. So I really do think that we're at a point where that realization is going to start to happen.
Got it. Veering into other topics, let's see, this was a question about additional infrastructure required for millimeter wave. Do you anticipate 5G handsets venturing outside of sub-6 gigahertz, or will millimeter wave technology be reserved for other markets? I mean, so maybe one of the questions is, how real is the millimeter wave part of 5G?
How real is the millimeter wave part? Well, people have certainly, I mean, Apple's new phone has millimeter wave parts in it. We've certainly seen Qualcomm has shipped a lot of millimeter wave parts. I'm not sure I understand where that question's coming from exactly.
No, neither do I. Maybe
So
the
it's,
person who asked.
you know, we know what we know there's a phone out there because Apple's selling us one.
Okay, but until we get the cells to support it, the
Well,
small cells.
you know, you've seen the ads on TV. Some of these
Yeah,
companies have already rolled them out. As I've said before in presentations, the AT&T rollout's been tied with the first responder network rollout.
right.
So that's been slower because AT&T is piggybacking on that money to roll out their expansion. So other companies that have not gotten that money are rolling it out, seem to roll it out a little bit faster. But that millimeter wave is rolling out. We talked to Ericsson and other companies, and they're selling millimeter wave systems. So this rolling out, but it takes time. I think we saw some rollout in 2020, but we're seeing more rollout this year. In other words, what I think my slide explained was that a lot of the rollout that happened in 2020 was in China at a sub-6 gigahertz, and we're starting to see more of the millimeter wave rollout now in the US and Europe.
Okay, that's good. Thank you. So somebody commented, "Hey, what about the poor lead frame? Didn't see a mention or lead
Yeah,
frame in any of your slides."
I mentioned it briefly.
Yeah.
We with our work with Semi, we have a chapter specifically devoted to lead frames and some of the challenges there. Those poor guys have not had price increases almost forever. Dan Tracy wrote that chapter, and you know, so certainly we've covered that. I just simply focused on a lot of the substrate business just for the lack of time. But yes, I did briefly mention that at the end, and those guys have been beat down as well, and that's why they've exited the business. They just can't make any money. So we you know we need to we need to treat everybody better here in the supply chain. We need to, you know, have a better relationships with each other.
So I wonder if anybody's done the analysis, what it would do the end product cost to raise the gross margin of the whole supply chain.
Well, you know, I think that's going to happen whether you like it or not. So
The price is going to go up. It's a
price is
question,
going
where's
up,
the,
folks. So get ready for it.
yeah, so it's just where does the money flow? Okay. Um, let's see, a lot of compliments, so great. Um, yeah, I mean, a lot of people are, actually now there's a question about 6G, and I think
Yes,
somebody
we
was,
started looking at 6G. 6G is I'd say that's 10 to 15 years out there on the rollout. There's a lot of research being done. There's certainly a tremendous amount of research, and we'll be discussing that in our next report. So feel free to tune in.
okay, got it. And speaking about Apple, you know, how about the adoption of ARM-based architectures for by other companies for desktop servers? Will, you know, are we likely to see ARM unseating the x86?
I'm not really able to comment on that as much. We have seen a lot of, obviously, a lot of ARM designs. So whether what happens over time is probably beyond something I can comment on at this stage.
Right. Well, and the breaking news this morning, Intel's going to have a new CEO. So,
Yeah.
yes,
Somebody must be worried
so
about something.
yeah. So, okay. There's a question about thermal management, and I don't know if you want to even venture into this, but do you see a new approach to thermal management? And probably
Yes,
it's,
that's a very good question. Very good question. Thermal management is becoming, we did a report last that we released in November that had a large section on the thermal um, issues. Because if you look at some of the designs these people are putting out there, some of these people are talking about 1,000 watts that they're going to try to dissipate.
right.
So there's real challenges in that, and that's why you need to try to come up with. Obviously, I think Paul Franzen used to say this, that the best thing you could do is design a chip that didn't have such a power dissipation. But you can combine some maybe packaging and some new materials and things like that to try to handle this better. But it's not received enough attention in the industry, and so I think there are people working on new materials to try to deal with this, and certainly that is something that I think moving forward we'll have to talk about a whole lot more.
Right. And we're certainly going to address the test aspects of that at Too Hot to Test in the
Right.
second week of February. So look forward to having people join us for that. Question on the alternatives for substrates, the fan in, fan out, all the different alphabet soup there. Is there one that's really picking up speed? They've been around for a few years. Obviously, they're lower cost
Yeah.
or they're portrayed, but do you see any really accelerating from the pack, or things that need to be done to get further traction on those?
Well, we've heard a lot of people talking about, since the M series technology's been put into production by ASC, and NEPIS is supposed to be bringing up a panel line in Korea. We've heard a lot of people talk about that. We know that Qualcomm is really driving a lot of this development, I think, or use, I would say, and this is there's some advantages that we talked about in a lot of our reporting on this, and I think that in that case there are people that are looking at that for a number of different reasons. But there's also capacity available for the EWLB type part, which has been qualified by a number of people. And what people used to say is, well, it's probably cheaper. These substrate prices have gotten so cheap that I can just do this flip chip on a substrate. But I'm not sure that that's going to hold true this year. So I think there may be people looking at some other options. And so in other words, it's an option that people are going to consider, and you're going to have to do all your trade-off analysis of it, and look at your designs and things like that to see what's possible and what's not. And if you could put it in a fan-in design, obviously that's what people would do.
All right, got it. You touched upon panel level packaging. This is a question asked about the competition between wafer level fan out and panel level. Will they coexist, or do you see like panel displacing building, on wafer? I mean, and somebody else asked, where do you think, what's the prospects of panel level packaging?
Well, I mean, we've seen a lot of people talk about, panel level packaging. Obviously, Simco had a production line, and that's what's their production line was able to produce the um, the combination application processor and PMIC that's in their watch. But and we have Nepes that's putting in a line in Korea using the M series technology. And the general idea is that if you do it in a large area panel, it can be cheaper. But you also have to yield it, because if your yields aren't high, then it's not cheaper. So, and it depends on what parts you're running. So, I mean, I think we've written extensively and talked about this, and I think obviously there's some interest, but it depends on what you're trying to do, where you're trying to do it, and the yield. And that's why I keep bringing up this discussion about yield, because that becomes terribly important in any of these discussions that we're having.
Yep, and it goes right to the bottom line. Okay. There are a bunch more questions. I think we've run to the end, but a lot of compliments. So thank you, Jan. It's always great to hear you. Just a reminder, we'll be posting the slides next week along with a video of the recording, and everybody who registered will receive an email. They'll let you know that those are available. Thank you very much, Jan. For
Thank
people
you.
who have further questions or need Jan's expertise, her contact information's up there. So it's always a pleasure. Thank you, Jan.
Thank you so much. Have a nice day and be safe out
Okay.
there.
Okay. So we would like to thank Torre and ASE for supporting today's Semiconductor Industry Speaker Series. So Torre Research Center in Japan was started in 1978. They have grown to be a professional technical services provider with cutting edge analytical equipment and 40 years plus years of accumulated experience in industrial fields such as semiconductors, electronics, and displays, batteries, fuel cells, and advanced materials, and others. They're currently engaging in state-of-the-art analytical services, contract R&D, and technical training. So if these are of interest to you, please contact Torre, and thank them for sponsoring today's presentation. And then we'd also like to thank ASE, who's a global leader in advanced semiconductor packaging and test with innovative technologies such as die interconnect, wafer level fan-out, embedded devices, conformal and compartmental shielding, integrated antennas, and others being refined and enhanced to support next generations of system integration. Their integration and miniaturization technologies are transforming solutions that are changing our lives from health to transportation, from robotics to AI, from IoT to 5G. Please thank them for their support. We thank both Torre Research Center and ASE Global for sponsoring today's Semiconductor Industry Speakers Series. And speaking about the series, please mark your calendar for January 27th and February 24th. We'll get out the announcements about the presenters as soon as possible. And then on March 10th, we have John Park from Cadence Design Systems talking about the difference between heterogeneous integration and system in package. And then also please mark your calendar. We'll have a great discussion over the 3 days for Too Hot to Test, the thermal management of large ICs during test. The schedule and registration are now available at events.meptec.org, and this is also a free event courtesy of our sponsors. And with that, I want to wish everybody a good day and thank you for joining us, and we look forward to seeing you at a future event. Thank you.